Understanding and applying Noether's theorem. Since high school, conservation laws have been our golden rules for solving physics problems. Problems like finding the kinetic energy of a pendulum or the velocity of an object after a collision become simple with the understanding that energy and momentum are conserved. While it makes intuitive sense that these qualities are conserved, if you ever stopped and asked why, you may have just been told, "That's how the universe works," and then felt fairly unsatisfied. Are energy and momentum always conserved? If not, what defines when they are and when they aren't? These are the same questions that mathematician Emmy Noether seek to answer in the early 1900s. Noether was considered a creative genius, and for the majority of her career she was concerned with abstract algebra, which people say gave her a uniquely generalized way of looking at problems that no other physicist had. Einstein famously said that she was the most significant mathematical genius produced since the higher education of women began. Noether had in fact helped define Einstein's theory of general relativity with what is considered to be one of the most well-respected laws in physics, namely Noether's theorem.
Noether's theorem states that for every continuous symmetry, there exists a conserved quantity and vice versa. There exists a one-to-one correspondence between the symmetry groups of a varying problem and conservation laws of its Euler-Lagrange equation. It also states that an infinitely dimensional variational symmetry group, depending upon an arbitrary function, corresponds to a non-trivial differential relation among its Euler-Lagrange equation. But what does this really mean? In order to understand this, we must first understand the principle of least action. Let's consider this situation. You walk into your living room and you see cake. Well, naturally, you're going to want to take the shortest path to the cake as possible. Now, the problem arises that there are multiple paths that can be taken. For example, you could take this path, or you could take a slightly more curved path. How do we minimize the energy and effort required to take this path? The answer to this is simple. Just take the Lagrangian. Now, what is the Lagrangian? It's simply Ke minus Pe in mechanics. This determines the path of an object in a system. In the Earth, the height corresponds to the object's Pe, and the horizontal speed corresponds to its Ke. Now, obviously, the shortest path would require a minimization of these two quantities. This is the same reason why in the Earth, the shortest path between 2 points would be a straight line. This minimizes the Lagrangian, as there is no Pe and very little Ke.